Tesla famously is working on Optimus, and when it comes to robotics, well, we all think we know a little bit because we've seen some science fiction films, but how much do we really know and how much is there to learn? Well, I have no idea, but I'm going to ask Dr. Scott Walter because he can fill in the gaps. I've come up with some pretty ridiculous questions that should hopefully come just to the verge of stumping him, and we'll get some good nuggets out of it. This is going to go real deep. I'm Brian. Welcome to Futurasa. Scott, so great to have you. You are in Zurich. That, makes you very neutral and chocolatey. I think that's how it works, right?
Yeah, something like that. And
Yeah.
so I understand this is the lightning round.
This this is because we'll get through as many as we can. Simulation versus reality. Now, you have been working in the robotics field for how long now?
I might almost be going into my fifth decade this year. Yeah.
Okay.
And so
You
over
have
40 years. Yep.
you have designed systems, you have built systems, factories, warehouses, all sorts of things. So you
Yes.
have more experience than anyone I've met, and more experience than most. And here you are. You're right here. Simulation versus reality. Have you ever had a situation where it looked good in the model and then you get out in the real world and it goes a little crazy? What was it and how'd you resolve it?
Okay. Yeah, that happens all the time. So a lot of times the simulation can look very, very convincing, and you go out in the real world, and it's like, why? My goodness, what's going on? And I think the one time I can think of, because you put me on the spot here, was uh, up in northern Finland, actually north of the polar circle. Umeå or Rovaniemi are very close to there, which is we're right on there. We were doing a water jet uh, project with a Fanic robot, and we were taking the nozzle going around a corner like that. And we were expecting it to follow that, and we went around. And we got like this really weird rippling that was happening. It's like, what's going on with that? Because it was just a short move. Now the thing with a robot is like when you're going like this, it may seem like a short move, but to the wrist is way up here, and it's suddenly going to come way around over there. So it's got this long move. In interpolation between robot joint space and Cartesian space is really weird that it actually has to interpolate between these different things. And so the joint movement, because some of these joints had to move a lot, actually resulted in it doing this and that. And once we got that information, we were able to kind of put that in and then tease it in, convince the simulation to show us that same effect. So a lot of times it came down to not quite modeling the way the control system behaved it right, actually controlled it, capturing that behavior and putting it in and then improving the simulation. So that, simulation is not the end all. You can think you know as much about it, but until you go out in the real world and get some empirical data, show you what's going on, it will never be 100%.
If you were to try and take a Sharpie and draw on the outside of a basketball, count how many times, how many different movements your hand needs to do to actually trace. I mean,
Mhm.
is that the problem you're describing?
Yeah, yeah, it's the kind of thing, and part of it is because think about it. I'm here and I'm trying to have to go around there. And you see my elbow is like moving really far. Everything's going there. So you're looking at that saying, I'm only going a couple of millimeters per second. I'm going and you understand when you go really fast, sometimes you'll get a lot of noise. But up here, these guys, they had to move like really far in a short period of time because you were expecting it to make that corner really quickly. And the result is it basically was pulling the pen off, kind of going back on where it's supposed to, as it was going around each time. And,
Okay.
and the thing with water jet is it reveals all your errors. If you're doing like
Oh,
a sealant application or spray painting or something like that, you don't quite notice it because the your actual TCP, the movement of that, puts down something very, very thick. But when you're in water jet cutting, you make a mistake, you see it right away. You look at the part and oh, that doesn't look right.
custom actuators. So Tesla with their Optimus, they went to the shelf. They went to the parts bin. They said, "What do you got?" And they're doing, of course, linear actuators. What is needed to determine what the actuator needs to be, then to make it, and why does it matter?
Well, a lot of it is in what they call inverse design. And the thing is that inverse design basically means you've got to find out what the characteristics of something that you want to have and then build the thing that's going to fit that. So what they had to do is say, we want to have a humanoid that's walking. In order to walk a certain speed, we kind of look at the accelerations and torques and velocities we need at each joint to be able to accomplish that for a variety of different common tasks it would have. Walking, stooping, carrying a load, something like that. And then you look at that whole thing and say, this is the kind of performance characteristics we need. Now, are there any motors out there that meet the spec? And then you go through the catalog and go, oh my God, they're not in here. Looks like we're going to have to design that ourselves. And you sit down. Now you have a lot of tension going on here in what you want to do. First you want to be able to get the performance that you need. But the other thing is like, I can give you any performance you want. Just provide me all the power. And then it's like, well, we got a limited power budget here too. So then
Right.
you got to kind of do something like that. We also got a limited mass budget. You got to keep it in the mass. Let's not make it too expensive either. So you've got all these things that are kind of at odds with one another to try to go in there and find what your right design space is. So the first thing you have to do is literally simulate what your bot is going to do, what the needs are. And now that you know the simulation is telling you this is how big a motor you're going to need, then you start to build those motors, and then you go out and you check them that you actually can get the performance that you need out of them.
Since they're designing their own robots, what do you think the voltage is going to be?
It's 52 nominal.
Okay.
Yeah,
Which is
we know that because they put it in a slide, and also we've counted the batteries and everything else, and the way they have it, I think it's 14 P10S or something like that. So we know the size of the battery pack. It's 2.3 kilowatt hours, and I think it's like I think it's 126 something like that. 4680s, not 46. Sorry, 2170s.
2170s. Yeah.
2170s. Yes.
And 52 is about the survivable limit if it shorts and you get zapped, I would imagine.
Yeah, I mean, basically it's 48. I mean, they say nominal because that's you have the nominal voltage. It actually can be a little bit higher when you're full state of charge, a little bit lower when you're low state of charge. What I pretty much think it means is that when it's near the very bottom of its level, it's going to be delivering 48. So I think that's really the system is running on 48, but it's kind of saying that you've got a supply that's going to be, you can calculate it as being 52.
And over 12 volt, that means I've got less weight and cost for wiring and less weight and cost for
Yes,
the actuators.
yes.
If I buy in
Exactly.
sufficient quantity, which
Right,
presumably they would.
right, right. And the fact that you've got like 10 of those strings also means you've built a lot of current that can deliver at the same time. So
Yeah.
each one of those things
Oh,
is delivering 52 volts for you. Or
gotcha.
sorry,
Separately.
I think it's 9 string. So I used to think it's 1410, but then there was like a CAD drawing. We went in there and then like started counting everything. It's like, oh, okay, it's 14 by 9. That seems to be what they actually have it.
You are the reason they can't show us more slides, I suspect. Uh, haptics in robots. First of all, what are haptics? And second of all, how does implementing haptics into a robot change what it can do?
Okay, so haptics is basically a sense of touch, and it will it could be very important because the robot needs to know when it comes to contact with something. The biggest problem they always had in robotics was a gripper that could pick up an egg without breaking it. Because and this is the idea of a multi-purpose gripper, a gripper that could go over and pick up something heavy and then come over and pick up something like an egg that was fragile and how to do it. And what you need to do is have a sense of haptic and feel of whether you're applying too much pressure and whether you come in contact with that. And the way most robots do it is they don't. They know I'm picking up a box that's this size, and they know if they get in this position and they close their fingers this amount, that they will just squeeze the box enough that they will have. And then if they're a little bit off center from the box will kind of push over to the other one and then they go down there. And again, that's not, there's no haptics in there. Now, what you could do is you could put a little bit of a force sensor on your paddles or
Mhm.
whatever they're closing down there and attempt to feel that force. There's another way you can do it without even putting in there is that you can measure the current that's going into your actuator. So when you're closing and you're not in contact with something, your current is one thing. And as soon as you come in contact, there'll be like a little spike, and that's considered like back EMF. And you could say, oh, if I look at that, I can kind of tell. So that's one version of haptics, but the other is actually putting a real sense of touch, because all the haptic tells me, or like I said, a back EMF is that like one of my fingers is coming in contact and is straining a little bit. It can't really tell me where it is along there and what the pressure point is. And so we saw the Gen 2 bot for Optimus. It looks like it has about 32 contact points that are on there. That looks like it has maybe about 7 different levels to tell the pressure. And that will tell you a little bit more about the object that you're picking up. And it'll help you to do things that do not require vision, that we do with a sense of touch. Now, we can do a lot just with our sense of touch. If you close your eyes, you'd be amazed at what you can do, what you can pick up. You have a feel of what the object is like. And, I love James Dama example that, the hand is so good. You put your hand in your pocket and count the change.
Yeah.
Uh, yeah,
That's a good
yeah. I mean,
example.
that's a great, that's
Yeah.
a really interesting kind of thing that we have. And now this could be very important. And there's a little bit of back and forth within the different community and what do you need it. Tesla started out saying we don't need it. Okay. And then they quickly said, oh, we think we need it. Figure started out without it and then said, you know what, looks like we don't need it. Now I think they're going to have it in there, but Brett had come out and said that, we started to do it and we were getting away basically with a back EMF for a lot of stuff. So there's like a question of how much you need. But I think, even figuring others are kind of comes back. There is importance to having that. And Milan even said in his last post when the new hand kind of came out there that they're getting ready to put haptics and everything else even more sensitive touch. You know, how sensitive it's going to be, where it all is, we don't know. Because once you put in there, it complicates it. There's wiring, there's all that other stuff in there. The other thing is that's a bit strange also is that we're not quite sure what it's going to be like for training. And that might be part of the reason they put it in there is if they have a really good data going, and usually a lot of gamers talk about haptics as like feedback. So you're in this virtual world and you hit something, you can't feel the force, right? Your hand goes right through the wall and you don't feel it.
Right.
Whereas in the real world, wow, that's going to hurt or something's going to push you back. And the best they can usually do is to have something vibrate in your hand to kind of let you know you've come in contact with it. So how do you take what, the real operator isn't feeling that object that's right in front of the operator. He's seeing it, he's going down there, showing off how to do it, but he's not getting that sense of touch. And will they be able to bring that sense of touch back to the operator so he feels the same thing? So you can kind of, to know whether that's going to be right. And that's going to be the trickiest part with teleoperation and how we're able to do that mapping. And it's one thing to say that, my arms are in the same configuration. This is what you need to do, but it's going to be something else to get that sense of touch. And that will be very important to get that nuance that you need to get that last, 10%. And we know that last 10% is usually seems like a lot more than the first 90%.
And we saw in one of the demonstration videos what looked like a heat map on the hand while it was performing an action, and that's what you're describing.
Exactly.
Yeah.
So that was that heat map that was showing it touching the egg, so I kind of knew where the egg was. And again, you kind of, there's more to it than necessarily it being blind. What you want to do is you want to map a sense of touch to what you're seeing. So you know what a certain object looks like. So a lot of times when you touch something, you know what that object is because you've seen it before. And that sense of touch brings back in your mind what it looks like, what you think you should be seeing if your eyes were open. So you do want to have the two together so you get this fusion between what you're seeing and what you're feeling and become very, very adept at that. And, a lot of times we will train ourselves that way. The famous things like trying to find a USB port in the back of my computer to be able to plug in. And,
Right.
if you kind of go through and teach yourself, what it feels like to put your finger over a USB port and look at it, it's like, oh, okay, I go back here and I know where it's going to be. But otherwise, if I'd never seen a USB port, I'd be like, ooh, what's that? I have no idea.
And it takes a while to figure which one is the network port versus the USB because they're pretty similar.
Yes.
We've all done
of course,
that.
the trick I do is I do the indentation. I stick my finger in there, and then I look at the indentation on the finger.
Oh, that's...
I go, oh, okay, that's that one.
I have learned something new. I've learned a bunch of new things, but that one somehow just tickles me. Let's talk about error handling. Now, prior to AI, error handling, I imagine, was something that you would need to go back in and code. But with AI, would you say that the example of not falling down on the slope is an example of error handling?
Yeah, that is because something happened out of the unexpected. Even the same thing when Tesla is driving and suddenly takes some sort of action to get out of an accident, it's because it's predicting this is how things are supposed to progress. And something is suddenly out of the norm. It's like, whoa, this is not what I was predicting. And same thing, you take that step. I'm predicting this is what my step is going to feel like. And my step suddenly feels very different. And I start to get that balance. I know, okay, I have to go through a bunch of things. Now, in the traditional way with error handling, you just look at like, what is the error? And there could be 3 or 4 different kinds of errors. It's like when you go to, you get the famous 404 error,
Right. Yes, of course.
There could also be a 410 error, which evidently
427,
there's
500.
Yeah. And the end effect is like the data's not there, but one reason is like couldn't find it or it was removed. It could be different examples of that. So the same thing is going to happen is that as you're going through this whole checklist of what is the error and what are the steps that I can do to recover if I can recover, and then you look at the other one. And so at some point it's like, do your best to not fall. Okay. and then you do a couple of actions to make sure you don't fall. But when you start falling, and they're all talking about this is the next thing I'm going to do, when you finally accept the fact I am about to fall, what's the best way to fall to minimize the amount of injury you would either do to yourself or the environment? And we all know how to do that. I hope, a lot of times we know like we'll cover our head or we'll duck and cover or we'll try to get into a roll. There's all sorts of things you can kind of do depending upon, how skilled you were in gymnastics as a kid. You'll have that instinct. And then the others are just the built-in instincts that when we slip and fall, our hands immediately go down. We don't think about it. Oh, that's the air handling case. And they're going to be
Hmm.
doing the same thing. And some of it may be that they start programming it in, or it may be that something the robots teach themselves when you do enough of this reinforcement learning and you put in one of the goals that, and when you do fall, try to not break. And then
Hmm.
you make sure the simulation comes back and says you don't break, which means, in a sense, we may be teaching these robots the concept of pain.
Well, the human instinct is if you're in a car crash, brace yourself. But
Hmm.
the rally car training says pull your arms in tight so that when it rolls, you don't lose an arm out the window.
Yeah.
Uh, because you have to know that this environment is a different one. Okay, so the last one, and this one is a doozy. I think it was you that said that while some mechanisms are easy to build, they're hard to actuate. Was that you?
Yes. 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 Yes.
Okay.
Yes. Yep.
Can you explain a design that you've worked on that was where this was particularly true and how your approach changed as a result?
Okay. Well, I mean, this is basically you see an example out there, and that is the human shoulder is a very simple method. It's a ball and socket joint, but it's really hard to actuate. And if you look at all the humanoid bots out there, you will not see a ball and socket there. You won't see it in the hip because the way to actuate it becomes very, very difficult. So you're looking in your toolkit of like, what are the different actuation strategies? Well, I know how to make a linear rotor, which is basically rotating about a cylinder. And I know how to make a rotary one and then linear axis, just go straight. And given that limitation, how do I go about actuating the different things I have to do? And they can become very complicated because you get space requirements that in there. A lot of times, if you use a linear actuator, it turns out if you have a constant velocity this way along your linear actuator, your rotational speed is not constant. It changes because it's got to go through this funky trigonometric kind of relationship to get that. So what that means is if you actually need a constant rotation on your joint, whether it's like your elbow joint or something like that, you have to have a very strange kind of profile on your linear axis where it has to be changing as a result of the inverse function of that whole thing. And so a lot of times that's why people would prefer to make the joint the rotary actuator because then it's very easy. It's a linear problem. People love solving linear problems. Non-linear problems become a little bit trickier. So again, the actuation strategy for the shoulder, no one's built a really good spherical actuator that I know of. And I've seen some
Mhm.
that are out there, but they just don't cut the mustard with what you'd really need. The closest that someone has come to, let's say someone that's embracing that, is clone robotics, where they're trying to rebuild the musculoskeletal system of the whole human body, and of course have that nice ball and socket joint in the shoulder that they're going to try to actuate with basically synthetic muscles.
Last time you were on the show, we talked about the ball and socket joints. In the comments, there were a few tips that I followed up on, and what I saw were some pretty neat designs that do not look reliable.
Yeah,
They look like they will do a fantastic demonstration, but that they would
yeah, yeah.
wear out
You can do it,
prematurely.
but you got to, what you would do is you might stick something up here, and then like along where your collarbone is, you could put a linear actuator that kind of pulls on that to kind of get it up, and then you need another one, and you're trying to get all 3 degrees of freedom. So they go around in different ways. And if you look
Sure.
at like the Terminator bot and what they showed in Hollywood, those are like examples of how you would do it. But you're right. The question is how reliable and how controllable they are.
Oh my gosh, you guys, we could do this all day, but at some point I have to get more coffee and probably use the restroom as a result of the coffee. Guys, what
Want me
did
to
we
get you one
miss?
from the Starbucks at the Zurich airport?
It was $11.11. I used my PayPal MasterCard so that I could immediately see the exchange rate. Yeah, because it's a Starbucks in an airport in Zurich.
Yeah.
That's a triple whammy.
Oh,
Uh,
no, and then quadruple is it's also in Swiss franc. which is like the strongest currency out there. So that makes it worse.
Oh, the exchange rate too. Yeah, I didn't
Yeah,
think of
yeah,
that.
yeah.
Yeah, so guys, what did we miss? What do we misunderstand? Leave it into them comments below. Dr. Scott Walter, thank you so much for joining us. And everybody else, please subscribe. It's how I convince the world that this channel is actually growing and working. It means a lot to me. It costs you nothing. And yeah, stay tuned, stay juicy. I cannot wait to hear from you clever robots on the next exciting installment. We'll get him back. You'll see.